Hello and welcome to Joe's Physics Corner. Today we're going to talk about deriving the Euler-Lagrange equation, which is basically the equation that describes Lagrangian mechanics. And before we do that, I am going to talk about the calculus of variations and what it means really to be optimizing a function L. So, before talking about a function L, we first have to talk about a function. How do we optimize a function? And so, I'm just going to give you an example. Let's say we have f of x. F of x, which looks like this. Simple, I'd say cubic. So this is f of x, and this is x. Well, what do we know? Well, we know that at this point and this point, we know that the gradient, the instantaneous gradient, which is d of f of x, so I say df over dx, is equal to 0. You know that in these points, the gradient is equal to 0. And how do we solve that? We solve this by, well, we basically differentiated this function and set that as 0, and we, well, in most cases we found the x value that gives the gradient of 0. And we said that, well, when we have x of this value, we said that we have optimized this function. We have found the minimum, either the minimum or the maximum point of this function over here. Now, when we have to do the same thing on a function L, things become a little complicated. And I'm going to tell you how to do that. Let's say we have an so a classic example of optimizing a function L is trying to prove why the distance. No, not prove, just evaluating or representing the distance of a curve, the total displacement of a curve, or the distance traveled along that curve. Like how do we get the length of a curve? That is our question, and that is going to be the equation I will use to explain what a function L really means and what it means to optimize a function L. And so I'd say, well, firstly, this is the x coordinate, and this is the y coordinate. I'm going to set 2 points here, and I'm going to set the x coordinate of this point as x1, and the x coordinate of this point as x2. And we said we're going to find the distance, the total distance traveled, the displacement, or along a curve. And so we could say, well, let's first draw the curve. We could say, well, the curve could look like that. It could be any curve. It could be a curve that looks like that, a curve that looks like that, whatever, or any continuous curve. And we're going to set that as a function called y of x. And we're trying to find the length of this curve. So how do we do that? Well, firstly, we're going to zoom in to any arbitrary sample point of this curve. I'd say about this point over here. And when I zoom it in, I would be able to see a straight line. And that straight line, when you continue it downwards, it's going to have some curve like that. But let's just assume that this is like when we zoom in infinitesimally closely to this curve, we're going to have in any point on this continuous line, we're going to have a straight line. And so that is the picture of that zoom is over here. And so how could we represent its instantaneous, I think, its instantaneous length in this section over here? Well, we could say that this is a right angle. You can say that this is dx, a small change in the x direction, the horizontal plane, and this as a small change in the y direction, and this as a small change in the displacement or the distance. It really doesn't matter here. All we are interested in is the length of this curve. And so we could say that this length over here it's a small change in the displacement. And what do we know by Pythagoras' theorem? Well, we know that the hypotenuse squared is equal to the addition of the square root of the two sides when it's a right angle. So we could say that, well, the s squared is going to be equal to the x squared plus dy squared. Can we simplify this? Or can we represent this in terms of s? Because s is basically what we are trying to find. Well, we could do that. First, we could, well, square root both sides and say that the s is going to be equal to a square root of the x squared plus dy squared. And then what could we do? Well, because this is a small change in s, by integrating it, we're going to integrate all of the small changes, and so we're going to get a full expression in terms of s. It's basically reversing a derivative to get the original function over here. And so we get s, which is basically integral of the s, is going to be equal to the integral, let's say from x1 to x2. So s is going to be equal to the integral of x1 to x2, because those are our limits those are our boundaries. Integral of the x squared plus dy squared. We're basically integrating both sides. And we don't like this expression over here because we are used to having dx at the end. Well, we're used to having the integral of f of x and d of x. We're used to having d of x at the end here. Because it's an addition multiplied by a small change to get the area in these cases. But here we're going to find, even though we're going to find the addition of the lengths, still it's going to be easier to say that dx is a multiplier because we're used to multiplying a small change. And so we could get dx out of this expression, or more, we're going to get dx squared out of this root here. So we're going to get dx isolated and get the square root of 1 plus dy over dx squared, because we're dividing both terms by dx squared, and get dx out here. And so we get a function, we get an expression that goes like that. S is equal to the integral of x1 to x2 of square root 1 plus dy over dx squared of the times d of x. Well, now, this is a form that we are really not used to do, because I'll give you an example. When we're trying to differentiate something, we're used to having something like x squared of d of x, where x here, the small change that we are multiplying, is always the variable that is present over here. However, when we look at this over here, this integral of x1 of x2, 1 plus dy over dx squared dx, we have so many variables. We not only have x, well, we do have x here, but we not only have x, we've got y here, and we could also argue that we have y prime, which is dy over dx, because obviously we have dy over dx over here. So we could say that this function L over here can be viewed in three different perspectives: x, y, and y prime. And what does that mean? It means that we're not having some function that depends on one value. We have something that depends on a function. We have a function that depends on a function that when we input a function into it, we're going to get some real number over here. Whereas in a classic function example, we're just going to plug in x and get a real value. Here we have to plug in a function such as x, y, or y prime. They're all functions. We said y prime is a function. We said y of x is a function. Therefore, y prime is also going to be a function, which is because y prime is a derivative of a function. So we have three functions that we have to input into to get a real number. And so that means it's not a classic function. What we're going to have is an example of a function L. And so what could we say this as? Well, we could say that the functional x will depend on variables y, x, y, and y prime, and it's going to give us the expression 1 plus y prime squared d of x. We're just saying that because this is equal to y prime, we're just going to say it as this. So that is our functional. That is the representation of our functional, the displacement functional of, in order to get the length of this curve. Well, now, so how are we then gonna find gonna prove that the shortest distance between this point and this point, which is obviously a straight line? How are we going to prove that it is actually a straight line? We know by intuition that it is going to be a straight line, but still we can't, we don't have a way to prove it, and this is one of the ways to prove it. So, as I said before, going back to the video, I told you that when we are trying to optimize a function, we're trying to find the point where dy of dx is equal to 0. And so, when we could put that into context, into a functional context, the same thing, a similar thing should make sense. We're trying to optimize, here we're trying to optimize y of x. And therefore, in this case, if we're trying to optimize the functional x, s of x, y prime, we're gonna have to be left in the end with an expression, or we're gonna have to find what function there are in order to satisfy the expression that ds now of something, which is gonna be d of x, of d of s of a change. I say d of change is going to be a 0 here, because and it's basically the same thing. Here the change is x. For a slight change in x, we're saying that the change in y, there's not even a small change in y. There is 0 small change in y. And so by the same principle, we're going to have to find what requirements there are for satisfying this value over here, that ds of d of some change is equal to 0. And the function that requires this situation, or this parameter, would be our answer to finding, and in this case, the shortest distance between this point and this point over here. And this concept called calculus of variations is not only useful when we're trying to find the shortest distance over here. A classic example would be proving why the brachistochrone curve would be in the form of a cycloid. It's not, the shortest path of descent from one point to one point is not going to be a straight line, but in the effect of gravity, it would be in the form of a cycloid. And the same thing could be used to do this. But today we're not going to do this. Today we're going to use this concept over here to derive the Euler-Lagrange equation. We're going to use the concept of calculus of variations to derive the Euler-Lagrange equation. Alright, so moving on to the Euler-Lagrange equation. So before we just showed that the following situation must be the case, that d of some variable, and in this case it's going to be the variance. So I'm going to write the change in variance over the change, a small change in anything, d of change, is going to be equal to 0. And because to make this a bit simpler with actual variables, we're going to just write this as ds. Okay, no, I'm not going to do this now. I'll just have this in mind. And so now let's move on to what Lagrange said about a general rule that defines the mechanics, or the motion of any object in the universe, that any object in the universe seems to follow, or he has proven. And it is that what Lagrange has proven was that the Lagrangian, the equation, the variable Lagrangian, which is given by the kinetic energy minus the potential energy, and with that Lagrangian we could define any object's motion. And to say this in a simple, kind of colloquial way, Lagrange has basically said that an object would follow any path that requires the least Lagrangian. And because Lagrangian is the difference between potential energy and kinetic energy and potential energy, we could say that any object would follow the path that requires the least variance in energy, the least change in energy. And so, what would that look like if we kind of graph it? Let's say we have a Cartesian plane. And there is the first coordinate here and the second coordinate over here. It's similar to what we did before. And this is the x and this is the y. Let's say that we have a curve. Let's say we already know the answer. And let's say we know the answer to how a certain object moves in a certain situation. Let's say that abstract curve that is the answer, that we know that it is the answer to, looks like anything. In this case, let's say that it looks like that. It's just any, it doesn't really have meaning. It's just, we're just assuming that this is the answer. Okay, then what could we say? Well, we know, what other curves that this object have gone through rather than this curve, this path over here? Well, it could have gone in any curves whatsoever that links, that starts here and ends here. So we could say that, well, it could have taken a similar but very different path like that. It could have, and it didn't, but it could have. And by proving that it does not take this curve, this path, we could say that this must be the answer. Okay, so first of all, we're going to say that this curve here is going to be y of x. Just defining it as y of x. And then, what could we say about this curve over here? Well, I'm going to say that this curve here, I'm going to say that the difference between this curve and this curve here and this curve here, could also be given as a function. And I'm going to say that, I'd say c of x, which is a change in the original function, so that difference here is going to be c of x. But that's not enough. By adding, we could express this line over here as y of x plus c of x, but then we are only bound to expressing only one curve, only one possible curve. But what we want is defining, disproving why any other form of a curve would not be the answer. And so having c of x is not enough. Let's say there is really an abstract curve that takes the form of a function that looks like that, or to keep it simple, I'd say something that looks like that. Well, now, how do we define that? This curve over here. We're going to say that the difference between this curve, the original curve, and this arbitrary curve that could have been any curve, I'm going to say that would be equal to epsilon times c of x. And epsilon here could be anything. It could be any function, any variable. But what we know that epsilon of c of x could now define any form of a curve, of a possible curve that this object that started from x1 and ended at x2 could have taken. Epsilon of c of x, the difference between that curve and the original curve, could be explained as epsilon of c of x. And so, if we say that this new curve is going to be a capital Y of x, we know that the capital Y of x would be equal to, well, y of x, the original curve, plus the change which we have given by epsilon c of x. And we could also say that big Y prime of x then would be, well, we're differentiating every term by x, so we get y prime of x plus epsilon of c prime of x. Well, what else do we know? Well, there's one important thing that we know, and that is that c of x of 1 would be equal to 0. Why? Because when you imagine that the cx goes to this point over here and cx here goes to this part over here, because we know that this object, regardless of the path it took, must have started from x1 and ended at x2, by moving x here, c of x, to x1, we're going to get a difference between this and that of 0. Here also 0. And so we get c of x1 is equal to c of x2, and they are both going to be equal to 0. And that's where we're going to start. All right, let's go back. Okay, now we have extracted everything from this graph, and we have these expressions over there. Now let's say let's say variance, which is a function L that depends on x, y, and y prime. Let's say that's going to be equal to the integral of x1 to x2 of the Lagrangian of x, y prime of d of x, of d of x. For now, it doesn't really make sense, because this basically what we have done is, from the equation, from the graph before that we used to display the shortest distance between 2 points and that any possible curve was possible, we got the expression that s of x, y, and y prime was equal to x1 to x2, if we're saying this is x1 and this is x2, of the square root of 1 plus y prime d of x. That's the equation we got. And we could do the same thing, the exact same thing, but set the Lagrangian as the function L that we are trying to optimize. Now you get the point, right? We're trying to optimize the Lagrangian. We're trying to find the path that minimizes the change in the Lagrangian, the integral of the Lagrangian. We're trying to optimize the integral of the Lagrangian. And so we're doing basically the same thing. And so we could express this function L over here, which is a bit different thing. But by doing a similar thing, we know that the Lagrangian would be equal to a function L that is given in terms of x, y, and y prime. So far, so good. Okay. And we knew here that the v of d of change is equal to 0. But what change would this be? What variable should we define this change here as? Well, from this graph, another graph that we used by having this original function, this initially changed function, and this massively changed function, we said that this this ultimate graph, big Y of x, it's basically, we could define this in terms of epsilon, right? Whatever value we give to epsilon, we could represent big Y of x as basically anything. And so epsilon is basically the variable we are trying to change. We're trying to find, well, what change in epsilon would give no change in the variance. And in that, when we find the conditions or the requirements for keeping that condition, we could basically get the solution to the Lagrangian mechanics. That's basically solving Lagrangian mechanics. What would give no change in variation when we change epsilon? That's basically what we're trying to find. All right, so now we could say, well, dv of the epsilon here, dv of the epsilon, which is equal to that, is going to be equal to 0. And now we know v. And so what would that be? Well, that would be, we have v here, so we're going to be integrating this in terms of epsilon. Wait. These have to be big Y's. Because big Y, the function big Y of x, is the function that we're trying to find. We're trying to find the function we're trying to find how big y of x would look like. That's basically what we're trying to do. We're trying to find the path of y of x that would be giving dv of the epsilon is equal to 0. And so we get the variables that we are trying to input in our function L's is going to be big y's and big y prime and x. All right, so we're going to derive this function in terms of epsilon. Well, this is basically v times the epsilon over 1 over the epsilon, and 1 over d over the epsilon. And so we get, because we have v as that, we get d of the epsilon times that here, because they are both equal, we get this expression over here. What could we say that is equal to? So before you do that, I'm just going to erase this part because I'm running out of space. Okay, and these I'm just going to transfer them down here because they're going to be important in the future. And c of x1 is equal to c of x2 equals to 0. All right. So we have this expression over here. D over d epsilon times integral of x1 to x2 of Lagrangian x comma y prime of d of x, and they're going to be equal to 0 over here. Okay. Because the variable that we're interested in this integral over here is x, what we could do is basically move this into the integral, because we could say that this is basically a constant because in terms of x, when we are dealing in terms of x. And so we get the integral of x1 to x2 of d of the epsilon of L x y prime of d of x is equal to 0. How can you simplify this? Well, we could, because we're derivating a function L in terms of a new variable, we could basically apply the chain rule, and we're going to get the partial L of partial of epsilon times partial of epsilon. Wait. Oh, no. We're going to get partial of L of partial of x times the partial of x of the partial of epsilon plus x, y, and y prime dx. We're going to get something like, when we apply the chain rule, L, Y. Yeah, we're going to get partial of L, because x is just a unit variable. We could say that this is equal to the partial of L of partial of y first, and times the chain rule, so the partial of y times the partial of epsilon plus the partial of L or partial of y prime times the partial of y prime of the partial of epsilon d of x is going to be equal to 0. All right, we have partial of y of epsilon here and partial of y prime of the epsilon over here. And we have the equations for both y and y prime here. And because we have them, it's going to be easy to differentiate them in terms of epsilon. So we get that would be equal to, well, if we're considering only epsilon as the variable that matters, so we're going to consider everything like that. So first, differentiating this here, y here, big Y here in terms of epsilon, the partial of y of the partial of epsilon. So we're going to get basically simply c of x, because we're considering that as a constant, and because epsilon here is going to be 1, we're only going to be left with c of x. And so that's going to be c of x, and that's going to be, with the same principle, we're going to eliminate that as 0, and then get only that part. So that's going to be c prime of x. Alright, then we could say that that's going to be equal to x1 to x2 partial L partial y times c of x plus partial L of partial y prime c prime of x dx is equal to 0. Alright, now what could we do? Well, let's look at this part over here. I have a feeling that we could apply integration by parts into the system over here to represent this part as something that is even simpler than this over here. So firstly, we're going to say that we could, because it's an integral, we could, divide the integrals by, because it's a plus, we could say, well, integral of that plus, we could divide the integrals into its constituent parts. So we get integral x1 of x2 lambda L over lambda y c of x d of x plus the integral of x1 of x2 lambda L lambda y prime c prime of x d of x is going to be equal to 0. And then we're going to look at this part over here. Alright, what does integration by parts tell us? Well, integration by parts tells us that when we integrate uv, we get the integral, basically when we have uv over here, when we integrate uv, when we differentiate uv, we get u prime v plus uv prime. And so we could integrate both parts and say that, well, uv is equal to integrate on u prime v plus uv prime. So we get u prime v would be equal to, there's no integration sign here because they're cancelled out, so we get uv minus uv prime. We do the same thing here. What are we going to set as our u prime? Well, u prime we're going to set as c prime of x because they're both something differentiated, so u, the result for u is going to be much simpler. So we get u prime, we're going to say u prime is c prime of x over here. So we get u will be equal to c of x, and then we're going to set v as here, which is the partial L of partial y prime, and v prime therefore would be dl over, it's going to be, because prime here we assume that we're differentiating in terms of x, so we get d over dx of partial L of partial y prime. That's what we're going to get for v prime. Alright, so basically we get this expression over here as be equal to uv, which is partial L partial y prime times c of x minus the integral of uv prime. U times v of prime. And so when we do that, it's going to be d over dx, so partial L partial y prime, c of x of d of x. That's what we're going to get. And we can't forget that this expression over here is going to be confined to x1 and x2. So only values x1 and x2 could go into this constant over here. Okay, so when we could say that this here now would be equal to, well, this part is untouched, so we write that as it is. So integral of x1 to x2 partial L over partial y c of x d of, just gonna get that in an entire integral sign, under the entire integral sign. So we get that. Oh wait, that's gonna be not easy. So we're just gonna leave it, okay, we're gonna leave it as individual parts. So we get that plus partial L over partial y prime. So we're gonna add this part, because this part over here is equal to this part over here, so we're going to add this here to this and get, well, we write it down exactly the same in terms of x1 and x2 minus the integral of x1 to x2 d of dx, partial L partial y prime of d of x. Okay, and that's going to be equal to 0. Okay, then because we have integrals both there and we said we're going to define this here as x, as the value for x could only be either x1 or x2. But what do we know? We know that c of x1 and c of x2 are both 0. So whatever value that's being inputted into x over here, either that's x1 or x2, the result is going to be 0. Because we said that c of x1 and c of x2 are both 0. Coming from the equation of the graph we drew, that the difference at the ends at x1 and x2 should be 0. And so this would be basically equal to 0. And so we could say that we could combine them into one integral finally and get, well, this over here, so partial L of partial y, c of x of d of x, not d of x goes at the end, minus the d of dx, so now it's this part, partial L of partial y prime, and now d of x. Oh wait, there's a c of x here, right? So there's going to be, I'm missing a c of x here, so it's going to be a c of x here too, of d of x is going to be equal to 0. Alright, that's what we have for now. So again, I'm going to erase all of that because we have simplified this version here in like that. And we're going to move on from here. Okay, so we have this expression over here. What could we do now? Well, we see that there are cx's here and there. So we could wrap this entire thing in terms of c of x and get integral of x1 to x2 c of x times c of x out, so only these parts are left. And we get this expression over here. And so now let's look at this over here. We have the integral of something is equal to 0. Integral of something is equal to 0. Well, it's quite a different concept, but for a simpler explanation, I'm going to consider the inside as just an ordinary function. Of course, it's not. It's going to be a function now, so it's going to be different. But to make it easier to visualize, I'm going to say that the inside is a function. And well, when the inside is a function and we integrate a function from one place to another, and the result is 0, we could say that, well, it's gonna be something like a linear and have, well, this point as x2 and this place as x1, so that the areas here and here are equal, and this is a positive, this is a negative, so we get a 0. Isn't this right? Well, of course it is right. However, the value we have set for x1 and x2, it shouldn't be a specific value. It shouldn't be something that, it should be interchangeable. x1 and x2, no matter what we do to x1 and x2, no matter, they're just arbitrary concepts. They're just arbitrary points in the Cartesian plane that we have set, but they are not fixed points. And so if you're going to solve this over here, it shouldn't, of course this makes sense. However, when we, consider moving this over here, so we get x1 over here. Now it doesn't make sense because, the area is don't add to 0. And so we could conclude that rather it should be something that looks like that. That looks like this, where of course the area under the curve must be 0 because fx is equal to 0. which means that the inside here must be equal to 0. And so we get the ultimate solution that the inside is 0. So c of x times this, the inside of the integral must be 0 in order to satisfy this over here. And what do we know by simple factorization that we learned in solving, polynomials? We know that when there are two things multiplied and the result is 0, either one of them must be 0. And so is the answer c of x is 0, or the right part is 0? Is that the answer that we want? Well, in first glance, it seems like it is the answer. However, we should go back to the graph we drew, in order to visualize this system, and we could then conclude that this would not be the case over here. So let's draw the diagram again. I think this is my fourth time drawing it. I'm really sorry. My board is just too small to get all the information I need. I'm really sorry. However, we get x1 over here, we had x2 here, we had the original function here, and we had the changed function like that. And maybe the once more change, the epsilon times the change would be that. And what we are interested here is that we call that as c of x. And so when we say that c of x is equal to 0, then this final graph would also be equal to 0, because epsilon, when you see y, big Y, is yx plus epsilon of c of x. But if when c of x is 0, then epsilon of c of x would also be 0. So big Y of x here would be equal to the original function we had. So, and we said that the original function is the answer. No, the original function is a function that we assume that is the answer to the question. And so basically when we say cx is equal to 0, we're not getting a condition. We're basically saying that the answer graph is equal to the answer graph, which does not tell us anything about the system. C of x being equal to 0, the final graph would also be looking like that. It's going to be exactly the same. So we're saying that the answer, well, when the question set tells us to find the answer, we say, well, the answer is the answer. We haven't really done anything. And so this here, although must be correct, it doesn't tell us anything about the system over here. And so here, this here would be our answer, and strangely enough, that is the Euler-Lagrange equation. But I don't want to end here. I want to move on. I want to change these variables, because I don't like y here and y prime. No. Wait, why is y prime over here? It was like that, so we don't have the y prime here. I'm sorry. It was y, it was just y here, so there's no y prime. And so, yeah, I like it, but I want to change these variables so that we get a more smoother or more generally applicable solution. So, what do we know about the relationships between y, x, and y prime? Well, we know that y prime was y differentiated in terms of x, so times d of dx. Are there anything, no, what if we set x here as time? Would it be still fine? Well, it's gonna be fine because x could be anything. X could be x could be, I don't know, anything. X could therefore also be time. X is just an arbitrary variable that we're changing, and because we could change time, especially when we're solving mechanics, Lagrange mechanics is a form of mechanics. Mechanics deals with the change of position in terms of time. So the concept of time is going to be really important. And so we're going to say that x is time, or given by t. All right, we're just going to erase all that now. And we're going to say that x is time. Well, are there anything that we could say that y prime be equal to y times d of dt? Like, is there anything that we get when we differentiate a variable in terms of time? Of course we have. We've got basically anything we could imagine when we say that y, well, we could say y is equal to the, I don't know, vertical displacement, no, the horizontal displacement. Then we get, well, the velocity, the horizontal velocity would be the horizontal displacement times d of dt. And so we could say that. We could say, well, then one form of Euler-Lagrange equation, or the equation we use for solving Lagrangian mechanics, would be, well, partial L of partial Sx would be equal to minus d of dx minus d of dt, because we were saying that t is the variable. Partial L of partial Vx, or we could say Sx of dot is equal to 0. That's one form. Or we could say, I don't know, we could say, if we're just going to deal with any arbitrary variable, let's say q, then we could say that, well, partial L of partial q minus d of dt, partial L of partial q dot would be 0. And that is, I'd say, the final form of the Euler-Lagrange equation, which could be used to describe basically anything, any mechanics, any motion of a particle, that be a photon or an electron, a ball, whatever, your body, whatever. But that rule applies, because that rule we have found is the rule that is applicable for a system that minimizes the change, the variance in energy, which is given by the Lagrangian. And so, yeah, that is the equation that describes Lagrangian mechanics. Q here could be anything. Q could be, I don't know, theta, and then Q prime would be, omega, or theta prime. It doesn't really matter what we use Q as, but what's important is that this equation must be satisfied, and basically any motion of any particle satisfies this equation, and therefore this could be used to model the mechanics, the motion of something. And yeah, that is basically the foundation of Lagrangian mechanics, which is the Euler-Lagrange equation, given like that, whereby Q could be basically any quantity that is differentiable in terms of t, because we have to multiply d of dt. And yeah, that's the end of my video. I hope you liked it. If you want to give any suggestions to my video, maybe there will be a problem in my speaking or my explanation. If you find any of them, please leave a comment below. I would be open to any suggestions. Also, please give me a like, subscribe, and yeah, see you on my next video. Maybe in my next video, I'm gonna see how the Euler-Lagrange equation could be used in real life or solving real physical situation problems. And yeah, I guess that would be my plan for my future videos. And again, thank you for watching. Give me a like, subscribe, and leave a comment below. Thank you very much. It was Joe's Physics Corner, dealing with deriving the Euler-Lagrange equation. Thank you.